Okay, here's the square from the first video that we've blown up so we can actually start calculating things. Remember, the idea is that we're just going to find, instead of finding the work done around the great big contour, we're going to pick one little rectangle on the inside, and we're going to calculate the work done by the vector field along each little rectangle. Now, the thing about it is, what we want to do is pick the rectangles so small that along each side, the arrows of the vector field are basically constant. So what we're going to do on this bottom side is we're going to plug in xy. We're going to get some sort of arrow for an answer. And we're going to calculate the work done by that arrow along the bottom side. Then we're going to plug in this right corner point. We're going to get a slightly different vector. And then we're going to use that vector to calculate the work done along the top. Now, to calculate the work done along the top, what I'm going to do, I could use this point over here, but it's got complicated coordinates. So what we're going to do is we're going to plug in xy plus delta y, and because the arrow is going to look like that, we're going to calculate the work done by that arrow along the top, and then to find the work done along the bottom, I can use any arrow I want to on that side. The assumption is that all the arrows on a side are roughly constant. I'm going to use the bottom one again. So this is what I'm going to do. I'm going to calculate the work done along each side. So what I'm going to do is call this side 1, call this side 2, call this side 3, call this side 4, and we're going to calculate the work done for by those arrows along each side. Now, for the work done along the bottom, what I need to do is I need to take the vector I get when I plug in xy. Well, we've got formulas for that. This is f1 of xy, I, plus f2 xyj. And what we want to do is dot that with a vector that goes directly along the bottom. Well, that's got to be some multiple of I. And we have to know how long it is. Well, usually a small change in x there is how we label those. So this is actually just delta xi. And so the work done by that red arrow pushing something along the bottom, remember j dot I is 0, so all that we're left with is f1 xy delta x. And that's going to be an estimate of the work done by our vector field pushing something along the bottom. And now I want to do pushing something along the right side. Well, let's find the work done along the right side. I need the vector that we're going to get along the right side. And so we plug in x plus delta xy into our formula. So we're going to get f1 x plus delta x y I plus f2 x plus delta x y j, like that. And I need to dot that with this vector that goes due north and has length delta y. Well, that's just going to be delta yj. That's not a surprise. When I dot those two vectors, the I part dotting with the j part is just 0, and all I'm left here is f2 x plus delta x yj, like that. Oop, not j. It's going to be delta y here, and there's a minus sign out front because of that negative out here. Nope, it's going to be positive. That's not a negative sign. All right, times. Now I want the work done along the top. Here we go. I think we can get this down here. I want the work done along the top. Now that looks like it's going to be mostly negative here, but meanwhile I'm going to be using that red arrow up at the top, and that red arrow is the vector f1 x y plus delta y I plus f2 x y plus delta y j dot, let's see here, I need a vector that's pointing due west this time, also length delta x. That's going to be minus delta x I, like that. Remember, the j part and the I part dot together to get 0, and so all I'm left with here is f1 x y plus delta y, I guess minus delta x. So I put a little minus right there, and then delta x like that. I'm going to go back to the top, and calculate the work done alongside 4. Alongside 4, what I said I was going to do, I'm hoping I'm going to live with this, I can use any arrow I want to on the left-hand side. We're assuming along each side the vectors are all pretty much constant. So I'm going to use the cheap, easy one. I'm going to use the arrow that I get by plugging in xy. So I'm going to get f1 at xy, I, plus f2 at xy, j, and I need to dot that with a vector that's going due south and has length delta y, so that's going to be minus delta y j. This is minus delta y j. We know that when we dot those two, the I part and the j part get 0, so all that we're left with here is minus f2 xy delta y, like that. Okay, so that's the combination of all the work we have from the all 4 sides. We're now going to try to combine these. Now, what am I going to do to combine them? I would like to look at, for example, the things that have y's in them. So let me put a little rectangle. Here is a term that has delta y in it. Here's a term that has delta y in it, and I'm just going to combine those two. I can combine them by pulling out a delta y, so what we're going to have here is, if I combine the delta y terms, I'm going to get f2, this is going to be x plus delta x, comma y, minus f2 of xy, like that, times delta y. Now, before we move on to the next term, let's just talk about this term a little bit. If you look at the top here, that looks like the top part of a difference quotient. Now, the only thing that's changing here is delta x. So if there was a delta x down here, we'd actually be looking at something that would be nearly the partial derivative of f2 holding y constant but letting x vary. So if there were delta x down here, what we'd really be looking at here would be the partial of f2 with respect to x. Now, I can't just throw a delta x down there. I can throw a delta x down there and throw a delta x up here, and so I'm going to get delta x, delta y, like that. So when I combine the two dy terms, I get almost exactly the partial of f2 with respect to x times delta x, delta y. Now, let's combine the things that have delta x in them. That's going to look like this, and that's going to look like this. Now, they both have delta x in it. I'm going to pull it out. I see that I want that top to look like a derivative, so I'm actually going to pull out a minus sign as well. If I pull out a minus sign, I'm going to get f1 x y plus delta y minus f1 xy, and we were pulling out a delta x. We wanted to say the same thing we did before. This looks like the top part of a difference quotient where only y is changing. If I was dividing then by delta y, this whole thing, since delta y is very, very tiny, would be almost exactly the partial of f1 with respect to y. So this would be roughly the partial of f1 with respect to y. But I can't just put a delta y down there. I can put a delta y down there as long as I put another delta y up here like this. And so I'm going to get delta x, delta y. So remember, all we're doing is calculating the work done around that one little rectangle. And around that one little rectangle, what we get is that amount of work plus that amount of work. And let's actually write this down as a conclusion way down here. Conclusion. That work is going to be almost exactly the same as partial f2 with respect to x minus partial f1 with respect to y, delta x, delta y, and we've successfully calculated roughly the work done around one little teeny tiny rectangle far inside the contour. But that is going to yield very good things.